In 1985, a geologist collected a bone from an Antarctic seabed and filled it as a large reptile. 40 years later, a CT scan revealed that it came from a titanosaur, the first dinosaur bone ever collected from Antarctica. The animal had lived in a warmer, forested Antarctica, then likely drifted out to sea after death. Its tailbone changed the continent's dinosaur history from inside a museum drawer. When scientists re-examined it in 2026, the fossil altered the history of Antarctic dinosaurs. The re-identification does more than correct a field label, it changes the history of Antarctic dinosaurs. The first dinosaur bone ever collected from Antarctica was already sitting in a drawer before anyone knew what it was. Its discovery forces a large question into view. If one of the continent's most historically important dinosaur fossils can wait for decades under the wrong name, how much of deep time is still waiting for the right question? The bone is cataloged as BAS D.8621.25. It is a partial vertebrae from near the front of a dinosaur's tail. It was collected on December 9, 1985, on James Ross Island, near the Antarctic Peninsula. The rock around it dates to 82.6 million years ago, give or take 500,000 years. That is more than 16,000 times the length of all recorded human history. Today, James Ross Island belongs to the familiar Antarctica of ice, black rock, wind, and long season of darkness. It is hard to imagine a place less inviting to a giant plant-eater, but the late Cretaceous continent was not the white desert of modern photographs. The Santa Marta Formation records flowering plants, ferns, conifers, and a climate far warmer than the one exists now. Older levels of the same formation preserve evidence for a mean annual temperature of around 19 degrees Celsius. That is not merely survivable, it is the temperature of a mild spring afternoon. Annual rainfall estimates range from 673 to 1991 millimeters, with wetter growing seasons comparable to those of modern tropical rainforests. Winter temperatures did not remain below freezing for long periods. At high southern latitudes, Antarctica was green. The contrast becomes even sharper elsewhere on the continent. A separate Cretaceous sediment core from the West Antarctic Shelf contains an intact network of fossil roots nearly 3 meters long, about as high as a basketball hoop. Those roots grew near 82 degrees south between 92 and 83 million years ago. They belong to a temperate lowland rainforest. Climate simulations match the ancient environment only when atmospheric carbon dioxide reached between 1,120 and 1,680 parts per million, and major Antarctic ice sheets were absent. This is the world in which the dinosaur lived, not an exact snapshot of one afternoon, and not proof that every corner of Antarctica looked the same. The continents were huge, climate change across distance and time, but the evidence is clear enough to overturn the old image. The Antarctic Peninsula supported warm, wet, vegetated landscapes capable of feeding large herbivores. Life at a high latitude still came with this strange rhythm. The sun's path changed radically with the seasons. Summer growing seasons could be intense, while long stretches of winter darkness altered the calendar of every plant and animal. Yet the climate evidence says this was not a landlocked beneath permanent ice. It was a place of soils, rainfalls, rivers, forest litters, and the steady conversion of sunlight into leaves. The dinosaurs' world was polar, but it was alive in a way the word Antarctica no longer suggests. Somewhere in that landscape, this Titanosaurus moves through the undergrowth. It is not one of the largest titanosaurs. The group includes animals heavier than 15 tons and longer than a city bus. This individual is estimated at only 6 to 7 meters long, roughly the length of a full-size pickup truck. It may have been a juvenile, it may have been a genuinely small adult. A single vertebrae cannot settle the matter. The limitation is part of the story. The bone does not tell us its color, its sex, its age, or the exact plants it ate. It does not preserve a skull full of teeth or a skeleton large enough to give us a species name. it gives us something smaller, and in its own way, more consequential. Proof that an advanced titanosaur lived in Antarctica during the Late Cretaceous. Titanosaurs were sauropods, members of long-necked dinosaur lineage that include some of the largest animals ever walked on land. The vertebrae has the characteristic architecture of an advanced titanosaurian tail. One articular end is cooped, the other rounded, part of a linked chain built to support a heavy tail behind a huge body. Its anatomy resembles fossils from other southern continents, especially South America. At some point, the animal died. The cause is lost. No tooth marks identify a predator. No fractured limb records a fall. No ash layer preserves a sudden catastrophe. The signs cannot force drama from a bone that does not contain it. The route from land to sea, however, leaves a plausible trail. Scientists think the carcass likely floated out from the coast after death. As the body broke apart, the vertebrae drifted into marine water and eventually sank. It landed among fish scales, shells, ammonite, plant fragments, and sediment on the ancient seafloor. The ocean buried a land animal. Mud packed around the bone, more layers followed, minerals moved through the buried tissue and turned it into stone. Over 82 million years, the sea became rock. The rock rose into landscape, and Antarctica changed from forested ground into a continent of ice. Almost the entire animal disappeared. Its tail vertebrae was the fragment that endured. In 1985, Mike Thompson of the British Antarctic Survey and Reinhard Forster collected that bone during fieldwork on James Rice Island. Their purpose was primarily geological. They were mapping rock layers and establishing a framework that would help later researchers date fossils across the region. The specimen came from a marine formation. It was found with marine and plant fossils. Thompson identified it reasonably as a large reptile. Nothing about that field label suggests carelessness. It reflects the information available at the time. Antarctica's dinosaur record was sparse. The fragment was incomplete. It came from a deposit better known for marine life. A tailbone in a marine fossil collection does not have an easy way to clarify its resume. BAS D.8621.25 then entered the collection, where it remained, and Antarctic dinosaur discoveries accumulated somewhere else. More of the continent's Mesozoic geology was mapped, and CT scanners became powerful enough to see inside dense fossil without cutting it open. Paleontologist Mark Evans later spotted the specimen in the British Antarctic Survey collection and suspected that it might be a dinosaur. His question began the formal investigation. Scientists did not identify the fossil by institution alone. They examined its external anatomy, compared it with other sauropods vertebrae, and CT scanned it at the Natural History Museum in London. The scan used 3,000 projections, each with an exposure time of 500 milliseconds. It produced a digital image with a voxel size of 0.06299 millimeters, roughly the thickness of the human hair. They also made a detailed surface scan of the bone. The resulting three-dimensional model could be rotated, measured, and compared with vertebrae from South America and other regions. Hidden chambers, proportions, and the shape of the articular surface all became evidence. We know this was a titanosaurian because its internal and external anatomy fit that group. We know where it came from because the original field notes and surrounding strata preserved its geological address. We know its age because ammonite biostratigraphy and radiometric dating constrain the beds around it. The scan does not conjure a complete dinosaur out of a fragment. It does something more reliable. It tests every visible feature against the anatomy of known sauropods. The bone's proportions can be measured to the smallest millimeter. Its internal structure can be inspected without a saw ever touching the fossil. Its three-dimensional shape can be compared with the specimens on the other side of the world. A museum drawer preserves the object. New methods allow the object to answer questions that did not yet exist when it was found. The final identification is deliberately cautious. Titanosauria interminate. An advanced titanosaurus? Yes. A named new species? No. The fossil is too incomplete for that. The researchers conclude that it belonged either to a juvenile or to a small-bodied adult. In paleontology, restraint is not a failure of imagination. It is the point where the evidence draws the line. Even at that limit, the implications are substantial. BAS D.8621.25 is only the second sauropod body fossil known from Antarctica. It is also the first dinosaur specimen known from the Santa Marta Formation. More importantly, although scientists formally described it only in 2026, it was the first dinosaur fossil ever collected from the Antarctic continent. The distinction matters because discovery has more than one date. There is also the day an animal dies. There's the day its bones enter the rock record. There's the day a person finds the fossil, and there's the day someone understands what the fossil is. Those dates can be separated by millions of years, decades, or single careful observation in a collection room. For Antarctica, the history of dinosaur discovery has now moved backward by a year. Other dinosaur fossils were collected later and recognized sooner. This vertebrae arrived first, but its meaning arrived last. The first chapter has been sitting in the archive while later chapters were already being published. The bone also adds weight to a larger idea about southern continents. During the Cretaceous, the fragments of Gondwana were still connected differently than they are today. Fossils from Patagonia, Antarctica, and Australia show that dinosaur populations occupied a changing network of southern landmasses. This one vertebrae cannot trace an exact migration route. It cannot prove that a particular herd crossed a particular corridor, but its titanosaurian affinities show that Antarctica was part of the story, not a blank space at the edge of the map. The continent was habitat. It may have been a bridge. It was a place where warm forests, coastal plains, and dinosaur population existed under a sky that would eventually hang above glaciers. That is why the mislabeled drawer matters. The word discovery usually suggests a dramatic excavation, a skeleton emerging from a cliff face, a field jacket opening after millions of years, a new species named under bright laboratory lights. This story is quieter. Its decisive moment may have been a scientist pausing over an old specimen and asking whether its first identification still made sense. No new bone had to be found. The past had to be recognized. The lesson is not that every forgotten fossil is a revolution. Most are not, but collections hold the raw evidence of earlier expedition, often gathered before the modern imaging, modern databases, or modern comparative studies existed. A label records what someone thought at one moment in time. The specimen remains available for the next moment. The Antarctic titanosaur waited through both. The discovery does not reveal a hidden army of dinosaurs beneath the Antarctic ice. It does something more useful. It shows how little the fossil discovery has to offer before someone learns how to read it. Antarctica still has the sparsest dinosaur record of any continent, largely because ice covers so much of its geology. Every exposed layer is a narrow window. Every fragment carries more weight because the archive is so incomplete. The missing animals may not all be buried in distant field sites. Some may already be in collections, cataloged under broad names, preserved beside fossils that once made more sense than they do now. Museum drawers are not graveyards for old science. They are libraries whose books are sometimes written in a language not yet understood. The animal, its forest, and the warm Antarctic landscape that supported both are gone. Their evidence remains. A root network preserved under the Antarctic shelf, leaves pressed into rock, ammonoids marking the age of a seabed, a partial tail vertebrae scanned more than 40 years after its discovery. Each is a small piece of a world that modern ice has almost erased. Antarctica was not always silent beneath the ice.